On September 14, 2015, at 5:51 in the morning Eastern Time, two identical facilities in Louisiana and Washington detected something extraordinary. For just a fraction of a second, space itself stretched and compressed as gravitational waves from two black holes that had collided 1.3 billion years ago finally reached Earth. The signal was so faint that it moved LIGO's mirrors by less than 1/10,000th the width of a proton. Yet this impossibly small distortion changed everything we know about the universe. What makes this even more remarkable is that within minutes, algorithms were already analyzing the data, confirming what human eyes would need hours to verify. The age of AI-assisted cosmic archaeology had begun. This is the story of how artificial intelligence became humanity's most powerful ally in detecting the most violent events in the universe, colliding black holes that send ripples through the very fabric of space-time itself. What started as Einstein's theoretical prediction over a century ago has evolved into a revolution where machines can now sense cosmic catastrophes happening billions of light years away. And they're getting better at it every single day. But this is more than a story about technology. It's about the profound partnership between human intuition and machine intelligence, a collaboration that has opened a completely new window on reality itself. Today, artificial intelligence has transformed how we hunt for these cosmic collisions. What once required months of painstaking analysis can now happen in real time. Algorithms process data streams that would overwhelm human researchers, identifying patterns in noise that would otherwise hide the whispers of distant black hole mergers. The technology has become so sophisticated that LIGO now detects a black hole collision approximately every 2 to 3 days during its active observing runs. Each detection is a cosmic event of staggering violence. Yet these catastrophes arrive with such regularity that we're building a statistical portrait of the black hole population across the entire observable universe. The journey to this moment began with Albert Einstein's general theory of relativity in 1916. Einstein's equations revealed something profound. Gravity is not a force in the traditional sense, but rather the curvature of space-time itself. Massive objects like stars and planets create dips and valleys in this four-dimensional fabric, and other objects simply follow the curves. It's as if the universe is a vast rubber sheet, and every massive object creates a depression that guides the motion of everything around it. But Einstein's equations predicted something even stranger. When massive objects accelerate through space, they don't just curve space-time locally. They create ripples that propagate outward at the speed of light. These gravitational waves are distortions in the geometry of the universe itself, compressions and expansions of space and time that travel across cosmic distances. Unlike light waves or sound waves that move through a medium, gravitational waves are the medium. They are space-time itself, oscillating. Imagine the universe as an ocean, except the water is space and time woven together. When massive objects collide, they create waves in this ocean. But these waves are unlike anything we experience in our everyday world. They don't push matter around. They reshape the very stage on which matter exists. A gravitational wave doesn't jostle atoms. It changes the meaning of distance between atoms. Einstein was so uncertain about the detectability of these waves that he spent years doubting whether they could ever be observed directly. He calculated that even the most violent cosmic events would produce waves so faint that measuring them would require detecting changes in distance smaller than the nucleus of an atom across kilometer-scale distances. The mathematics was elegant and compelling, but the experimental challenge seemed insurmountable. For decades, gravitational waves remained a theoretical curiosity, a prediction that most physicists believed would never be verified through direct observation. The first indirect evidence came in 1974, when Russell Hulse and Joe Taylor discovered a binary pulsar, two neutron stars locked in a tight orbit around each other, spinning dozens of times per second and emitting beams of radio waves like cosmic lighthouses. By precisely tracking the arrival times of these radio pulses over months and years, Hulse and Taylor noticed something extraordinary. The two stars were gradually spiraling inward, losing energy at exactly the rate Einstein's theory predicted for gravitational wave emission. The neutron stars were radiating away their orbital energy as gravitational waves, invisible ripples that carried momentum and energy across the galaxy. And this discovery earned them the 1993 Nobel Prize and provided compelling evidence that gravitational waves existed, even though no one had detected them directly. The universe was confirming Einstein's equations, but in a frustratingly indirect way. But detecting gravitational waves directly required building the most precise measuring device ever conceived. The challenge was staggering. To detect a gravitational wave, you need to measure changes in distance smaller than 1,000th the width of a proton across distances of several kilometers. It's like measuring the distance from Earth to the nearest star, and being able to detect if it changed by the width of a human hair. No existing technology came close to this precision. Every vibration, every thermal fluctuation, every quantum jitter of atoms would dwarf the signal being sought. The universe itself seemed to conspire against detection, filling the environment with noise that would mask the faint whisper of distant cosmic violence. 3 visionary physicists made this seemingly impossible measurement achievable. Rainer Weiss at MIT developed the theoretical foundation for laser interferometry as a gravitational wave detector, working out the noise sources and mitigation strategies in exquisite detail. Kip Thorne at Caltech provided the theoretical understanding of what gravitational wave signals would look like, collaborating with relativists around the world to predict the exact waveforms that different cosmic events would produce. Ronald Drever, also at Caltech, pioneered many of the experimental techniques needed to build such sensitive instruments, developing innovations in laser stabilization and mirror suspension that pushed measurement precision to unprecedented levels. Later, Barry Barish joined the effort and transformed LIGO from a physics experiment into a massive engineering project, building the organizational structure and industrial partnerships necessary to construct something this complex. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 identical facilities separated by thousands of miles. Each detector uses laser light traveling down 4-kilometer-long arms to measure tiny changes in distance. The principle is deceptively simple. Split a laser beam in 2. Send the beams down perpendicular arms, bounce them off mirrors, and recombine them. If both arms are exactly the same length, the light waves arrive back in perfect sync and cancel each other out. But if one arm becomes slightly longer or shorter than the other, the light waves fall out of sync and produce a detectable signal. When a gravitational wave passes through, it alternately stretches and compresses space itself, causing one arm to lengthen while the other shortens by an infinitesimal amount. The mirrors don't actually move. Space itself between the mirrors expands and contracts. The engineering challenges were immense and required solving problems that had never been encountered before. The mirrors had to be isolated from every possible source of vibration. Earthquakes thousands of miles away, truck traffic on nearby highways, even the gravitational effects of clouds passing overhead. Each mirror weighs 40 kilograms, but is suspended by impossibly thin glass fibers that allow it to hang like a pendulum, isolated from ground motion. These suspension systems use multiple stages, each filtering out different frequencies of vibration. The final mirror acts as if it's floating in space, responding only to the stretching and compression of space-time itself. The laser beams travel through ultra-high vacuum chambers, where the air has been pumped out to pressures lower than outer space. Any residual gas molecules would scatter the laser light and create noise. The vacuum system is so extensive that it contains over 10,000 cubic meters of volume, making it one of the largest ultra-high vacuum systems ever constructed. Every weld, every seal, every component had to be engineered to maintain this extreme vacuum for years at a time. The mirrors themselves are marvels of precision. They're made of synthetic fused silica, polished to within a few atoms of perfect smoothness. Their surfaces are coated with alternating layers of materials that reflect 99.9999% of the laser light, allowing the beams to bounce back and forth hundreds of times and effectively increasing the arm length to thousands of kilometers. Even the thermal noise of atoms randomly jiggling in the mirror creates fluctuations that must be carefully characterized and subtracted. At LIGO's most sensitive frequencies, the mirrors are cooled and their thermal noise is predicted and removed using sophisticated algorithms that model the material properties at the quantum level. The project took decades to complete and cost over $600 million, making it the largest single project ever funded by the National Science Foundation. Construction began in 1994, requiring the excavation of massive trenches in the Louisiana Bayou and the high desert of Washington state. Each arm is housed in a concrete tunnel 4 feet in diameter and 4 kilometers long, running in perfect straight lines across the landscape. The two facilities are separated by over 3,000 kilometers, a crucial design feature that allows scientists to verify that detected signals are truly cosmic in origin and not local disturbances. Initial LIGO operated from 2002 to 2010 without detecting a single gravitational wave. The sensitivity simply wasn't enough. Scientists could set upper limits on how often black hole mergers occurred, but they couldn't actually see any. This was a frustrating period for the collaboration, spending years operating exquisitely sensitive instruments that found nothing but noise. But the team persevered, learning about every subtle source of vibration and interference, cataloging glitches and artifacts, building a deep understanding of how the detectors behaved. A massive upgrade called Advanced LIGO increased the detector's sensitivity by a factor of 10, expanding the volume of space it could survey by 1,000-fold. More sensitive lasers, better mirrors, improved suspensions, and enhanced seismic isolation transformed the instruments. The laser power increased from 10 watts to 200 watts, allowing for better statistics in the photon counting. A new active control systems used hundreds of sensors and actuators to keep the mirrors perfectly positioned. The entire detector became a symphony of feedback loops, constantly measuring tiny disturbances and applying precisely calculated corrections. Then came that historic morning in September 2015. Advanced LIGO had been operating for just a few days, still in its engineering run phase, when both detectors simultaneously registered a characteristic pattern: the unmistakable chirp of two black holes spiraling into each other. The signal arrived at the Louisiana detector 7 milliseconds before reaching Washington, a time delay consistent with a gravitational wave propagating at the speed of light across the continent. The signal was so clear and unexpected that many scientists initially thought it might be a test injection, a fake signal inserted to verify the system was working properly. For several tense hours, a small group of senior scientists checked whether anyone had deliberately injected a hardware signal. They had not. This was real. The two black holes that created this signal were approximately 29 and 36 times the mass of our Sun, far more massive than any stellar black hole previously known in our galaxy. They had been orbiting each other for billions of years, gradually losing energy by emitting gravitational waves and spiraling closer together. For most of this time, the gravitational waves they emitted were too weak to detect, too low in frequency for LIGO's sensitive band. But in the final moments before collision, everything changed with staggering speed. As the black holes drew closer, they accelerated, orbiting each other faster and faster. The gravitational waves they emitted grew stronger and higher in frequency, sweeping upward through LIGO's detection band in a characteristic pattern called a chirp. In the last tenth of a second before merger, the black holes were orbiting each other dozens of times per second, whipping around at nearly half the speed of light. The space-time around them became violently distorted, warped into shapes that defy visualization. The black holes themselves were no longer separate objects, but rather two colliding regions of infinitely curved space-time, their event horizons deforming and stretching before finally merging into one. At the moment of merger, 3 solar masses worth of matter converted into pure gravitational wave energy in just a few tenths of a second. And to put this in perspective, for that brief moment, the power output in gravitational waves exceeded all the light from all the stars in the observable universe combined. Every photon from every star, every quasar, every galaxy, all of it produced less power than this single black hole collision. Yet this enormous energy release was essentially invisible. No light was emitted because black holes, by definition, emit no light. The entire event occurred in pure gravitational waves, a form of radiation that humanity had never directly observed before. The waveform detected by LIGO contained an extraordinary amount of information encoded in its precise shape. The initial frequency of the chirp revealed how far apart the black holes were when they entered LIGO's detection band. The rate at which the frequency increased indicated the combined mass of the system. More massive black holes spiral together faster in the final moments. The amplitude of the signal revealed the distance to the source. Because gravitational waves, like all forms of radiation, grow weaker with distance, the duration of the signal indicated the mass ratio of the two black holes. Because equal mass systems merge differently than unequal systems, even subtle features in the waveform carried information. Small deviations from a simple chirp revealed that the black holes were spinning, rotating on their axes as they orbited each other. The direction and magnitude of these spins left specific imprints on the gravitational wave pattern. After the merger, the signal didn't simply end. Instead, it exhibited a ring-down phase, where the newly formed black hole vibrated like a struck bell, gradually settling into its final spherical shape. These oscillations, called quasi-normal modes, have frequencies determined entirely by the mass and spin of the final black hole, providing an independent verification of the merger dynamics. This discovery, announced to the world on February 11, 2016, opened an entirely new window on the universe. For the first time, humanity could observe cosmic events through space-time itself rather than through light. Gravitational wave astronomy was born. The three founders of LIGO, Rainer Weiss, Kip Thorne, and Barry Barish, were awarded the 2017 Nobel Prize in Physics for their decisive contributions to this revolutionary achievement. But the detection also marked the beginning of something equally profound: the integration of artificial intelligence into the very heart of astronomical observation. Even as LIGO revolutionized astronomy, researchers recognized that artificial intelligence could make the detectors far more powerful. To understand why, we need to appreciate the fundamental challenge of gravitational wave detection: finding an incredibly faint signal buried in enormous amounts of noise. The data streaming from LIGO's detectors contains thousands of samples per second, each recording the detector's response with exquisite precision. Most of this data is noise. Random fluctuations from quantum uncertainty in the laser light, thermal jitter of atoms in the mirrors, seismic vibrations, electromagnetic interference, and countless other sources. The gravitational wave signal, when present, is a tiny oscillation riding on top of this noise ocean. Traditional analysis methods rely on a technique called matched filtering, a powerful but computationally demanding approach. Matched filtering works by comparing the detector data against a library of theoretical waveforms, testing whether any template matches the observed pattern well enough to indicate a detection. This requires having accurate predictions for what gravitational wave signals should look like, which in turn requires solving Einstein's equations for different types of cosmic collisions. For black hole mergers, these equations are so complex that they can only be solved numerically using supercomputers, a field known as numerical relativity. Numerical relativity simulations begin with two black holes in orbit and evolve Einstein's equations forward in time, calculating how the space-time geometry changes as the black holes spiral together. These simulations are extraordinarily challenging because Einstein's equations are 10 coupled nonlinear partial differential equations describing how space and time curve in response to matter and energy. The equations must be solved on a three-dimensional grid covering the region around the black holes, with time stepping that captures the rapid dynamics of the final moments before merger. A single high-accuracy simulation can require weeks of computation on hundreds of processors. To build a comprehensive template bank for matched filtering, these researchers need to simulate thousands of different scenarios. Black holes with different mass ratios, different spins pointing in different directions, different orbital configurations. Each variation produces a slightly different waveform. The template bank must cover this entire parameter space densely enough that no real signal falls through the gaps. For binary black hole systems, the relevant parameter space is effectively 9-dimensional, including the masses of both black holes, the magnitude and orientation of each spin, and the distance and orientation of the system relative to Earth. The computational burden is staggering. Processing a single second of LIGO data through the full template bank requires comparing the data against tens of thousands of waveforms, each involving Fourier transforms and correlation calculations. For continuous operation generating thousands of seconds of data per day, this represents a substantial computational challenge. Traditional matched filtering pipelines distribute this work across computing clusters. But even with significant resources, the analysis can lag behind real-time by minutes or hours. This is where artificial intelligence enters the story, fundamentally transforming the search for gravitational waves. The first major AI breakthrough came through deep learning algorithms that could rapidly identify gravitational wave signals in noisy data without explicitly comparing against template banks. Daniel George and E.A. Noyuerta at the National Center for Supercomputing Applications developed a technique called deep filtering using convolutional neural networks, the same type of AI used for image recognition and computer vision. Their approach was elegantly simple in concept, but profound in implications. Instead of treating gravitational wave detection as a template matching problem, they reframed it as a pattern recognition problem. Convolutional neural networks excel at finding patterns in complex data. Given enough training examples, these networks can learn to recognize gravitational wave signals even when buried in realistic noise. Without needing explicit templates, the network learns what features of the data are important and which are irrelevant, developing an internal representation optimized for detection. Training the network required generating hundreds of thousands of simulated gravitational wave signals and injecting them into real LIGO noise. Each training example consisted of a short stretch of data, some containing signals and others containing only noise. The network learned through repeated exposure, gradually adjusting its internal parameters to maximize detection accuracy. The training process used backpropagation, an algorithm that computes how small changes to each network parameter would improve performance, and iteratively refines the entire system. The results were striking. The deep learning system could detect black hole mergers in real time with sensitivity matching traditional methods while being thousands of times faster computationally. What required hours of computing cluster time with matched filtering could be accomplished in milliseconds on a single graphics processor. This speed advantage is crucial because gravitational wave astronomy works best when detectors around the world can quickly alert other telescopes to look for light from the same cosmic event. When LIGO and Virgo detected the collision of two neutron stars on August 17, 2017, an event designated GW 170817, the real-time analysis pipeline sent out alerts within minutes. Telescopes around the world turned toward that patch of sky within hours, observing the explosion across the entire electromagnetic spectrum from gamma rays to radio waves. This multi-messenger astronomy provided a much richer understanding of the event, revealing that neutron star mergers are the primary production sites for heavy elements like gold and platinum. The rapid gamma ray burst, the optical kilonova that evolved over days, and the X-ray and radio afterglow that persisted for months all contributed to a comprehensive picture of the physics involved. But this multi-messenger success story depended critically on rapid gravitational wave detection and sky localization. Gravitational waves pass through the detectors over a span of several seconds, and the signal arrives at different detectors at slightly different times, depending on the source direction. By analyzing the arrival time differences and comparing signal characteristics between detectors, researchers can estimate which region of the sky the waves came from. However, this localization is typically quite uncertain, covering hundreds or thousands of square degrees. AI algorithms have dramatically improved sky localization accuracy by quickly processing data from multiple detectors in the global network. LIGO's 2 detectors in the United States are now joined by Virgo in Italy, Kagra in Japan, and eventually LIGO India. Each additional detector significantly improves angular resolution. Machine learning systems can rapidly perform the complex statistical analysis required to combine information from all available detectors, producing sky maps that guide electromagnetic telescopes to the most probable source locations. The localization problem is fundamentally a Bayesian inference task. Given the observed data and our understanding of detector noise and signal properties, what source parameters are most probable? Traditional Bayesian parameter estimation uses Markov chain Monte Carlo sampling or nested sampling algorithms to explore the parameter space, but these methods require hours or days to converge. AI approaches can approximate these calculations in seconds by training neural networks to perform Bayesian inference directly, learning the mapping from data to posterior probability distributions. As LIGO collected more data, AI applications expanded beyond just signal detection. Machine learning algorithms now classify the various types of noise that can contaminate gravitational wave measurements. Environmental factors like earthquakes, human activity, and even weather patterns can create artifacts that mimic gravitational wave signals. LIGO's detectors are exquisitely sensitive to ground motion, decoupling to seismic waves from earthquakes anywhere on Earth. An earthquake in Japan can create noise in the Louisiana detector. Ocean waves pounding against distant coastlines generate microseismic noise that propagates through the crust. Nearby logging operations, construction sites, and even automobile traffic contribute vibrations. But the noise isn't limited to seismic sources. Electromagnetic interference from power lines and radio transmitters can couple into the detector's electronics. Lightning strikes thousands of miles away can induce current fluctuations that appear as glitches in the data. Cosmic rays striking the photodetectors create brief spikes. Scattered light within the vacuum chambers interferes with the main laser beam, creating fluctuations that depend on air density variations and temperature gradients. Each of these noise sources has a characteristic signature, but distinguishing them from real gravitational wave signals requires careful analysis. The Gravity Spy project represents a fascinating collaboration between artificial intelligence and citizen science. Volunteers examine images of potential gravitational wave signals, helping to classify different types of noise. The data is presented as spectrograms, visual representations showing how the detector's signal strength varies with time and frequency. Different glitch types create distinctive patterns. Blip glitches appear as brief bright spots. Scattered light glitches create characteristic arches. Whistle glitches sweep upward in frequency over several seconds. Human volunteers learn to recognize these patterns and labeled thousands of examples. Their classifications train machine learning algorithms that become increasingly sophisticated at identifying and rejecting false signals. Since 2016, tens of thousands of volunteers have provided over 7 million classifications, dramatically improving LIGO's ability to distinguish real gravitational waves from instrumental artifacts. The AI system builds on this human expertise, learning the subtle differences between glitch types and developing the ability to classify new glitches with high confidence. Some glitches are so characteristic that they can be flagged and removed automatically. Others require more careful investigation. The glitch classification system uses convolutional neural networks trained on labeled spectrograms. These networks learn hierarchical representations, with early layers detecting simple edges and patterns, while later layers recognize complex combinations that identify specific glitch types. The system achieves over 98% accuracy on known glitch categories and can identify novel glitch types that don't match existing classifications, alerting human experts to investigate new instrumental problems. This automated quality control is essential because LIGO generates thousands of data segments every day, and even a small false alarm rate would produce many spurious triggers that waste observational resources. By accurately identifying and vetoing glitches, AII systems ensure that telescope alerts are reliable and that follow-up observations focus on genuine cosmic events rather than instrumental artifacts. Recent advances have pushed AI's role even further. In a collaboration that exemplifies the synergy between cutting-edge AI research and fundamental physics, Google DeepMind worked with LIGO scientists to develop a technique called deep loop shaping that uses reinforcement learning to actively control the detector's mirrors. This represents a fundamentally different application of AI, not just analyzing data, but directly operating the instrument to improve its performance. LIGO's mirrors must remain perfectly still to measure gravitational waves, but they're constantly buffeted by noise. Traditional control systems use feedback loops to measure mirror motion and apply corrective forces, but these systems are limited by classical control theory. The mirrors have complex mechanical resonances, and controlling motion at some frequencies can inadvertently amplify motion at others. Designing optimal control systems requires balancing multiple competing objectives, and the parameter space is too large for human intuition to navigate fully. The DeepMind team approached this as a reinforcement learning problem. They created a detailed simulation of the LIGO detector, including the mirror dynamics, suspension systems, and noise sources. The AI agent's goal was simple: keep the mirror as still as possible. Its actions were adjustments to control system parameters that determine how forces are applied to the mirror. The reward signal was the reduction in mirror motion, measured across all relevant frequencies. Researchers ran dozens of simulated LIGO detectors in parallel, allowing the AI to explore millions of possible control strategies. The agent tried different approaches, learning from successes and failures, while gradually discovering techniques that human engineers had never considered. The reinforcement learning algorithm used is a variant of deep Q learning, where a neural network learns to predict the long-term value of different actions given the current state of the detector. The result is a system that can quiet the detector's most challenging noise sources in ways that traditional methods simply cannot match. Traditional control systems can reduce mirror motion by a certain amount, but the AI system achieves improvements 30 to 100 times greater at some frequencies. This dramatic noise reduction allows LIGO to observe black hole mergers that would previously have been too weak to detect, effectively increasing the detector's sensitive volume and the rate of discoveries. The success of reinforcement learning in mirror control has inspired researchers to explore AI optimization for other aspects of detector operation. Machine learning algorithms now help tune the laser frequency stabilization systems, optimize the alignment of optical components, and adjust the balance between different noise reduction strategies. The detector has become a complex adaptive system where AI continuously fine-tunes performance parameters based on changing conditions. Meanwhile, at the Max Planck Institute for Gravitational Physics in Hanover, Germany, researchers developed an AI algorithm called Urania that designs entirely new types of gravitational wave detectors. Rather than optimizing existing designs, Urania explores a vast space of possible detector configurations, discovering both known techniques and completely novel approaches that could improve sensitivity by more than an order of magnitude. The design space for gravitational wave detectors is immense. Beyond the basic interferometer configuration, there are quantum noise reduction techniques like squeezed light injection, alternative mirror materials with lower thermal noise, different laser wavelengths, novel suspension designs, and exotic proposals like cryogenic cooling or crystalline coatings. Each design choice involves trade-offs, and the optimal configuration depends on which noise sources dominate at different frequencies. Urania uses evolutionary algorithms combined with neural networks to navigate this design space. The system generates detector designs, simulates their performance, evaluates how well they would detect gravitational waves, and uses this feedback to evolve better designs. Over many generations, the algorithm converges on configurations that maximize detection sensitivity within realistic constraints on cost and technical feasibility. Some of the designs Urania proposes match known advanced concepts that researchers have developed independently, validating the approach. Others are genuinely novel combinations that human designers hadn't considered, suggesting new research directions. This AI-driven detector design is particularly valuable as the field plans next-generation observatories. The proposed Cosmic Explorer in the United States and Einstein Telescope in Europe will be far more ambitious than current detectors. With arms 10 to 40 kilometers long and sensitivity improvements of 10 times or more, these facilities will detect thousands of black hole mergers per year, observing collisions throughout cosmic history back to when the first stars formed. The Einstein Telescope will be built underground in a triangular configuration with 3 interferometers, providing better seismic isolation and the ability to measure both polarizations of gravitational waves simultaneously. The underground location naturally provides temperature stability and protection from surface disturbances. The detector will use cryogenic cooling to reduce thermal noise in the mirrors, operating at temperatures just a few degrees above absolute zero. This introduces new technical challenges, but dramatically reduces the random jitter of atoms in the mirror material. Cosmic Explorer will push the interferometer concept to its ultimate scale on Earth's surface, with 40-kilometer arms stretching across the landscape. At this scale, the curvature of the Earth becomes a factor in the design, and the vacuum chambers must be precisely aligned to account for the planet's spherical shape. The longer arms provide proportionally greater sensitivity, allowing Cosmic Explorer to detect smaller black hole mergers and observe events at greater distances. Both detectors will rely heavily on artificial intelligence for operation and analysis. The data rates will be enormous, far more than human analysts could process, and the detection rate will make manual inspection of every candidate event impossible. AI systems will provide real-time classification, rapid parameter estimation, and automated quality control. Machine learning algorithms will identify particularly interesting events for detailed follow-up, flagging unusual masses, spins, or other properties that might indicate new physics. The computational infrastructure required is itself remarkable. LIGO's data pipeline currently processes information from multiple detectors using dedicated computing clusters with thousands of cores. Graphics processing units accelerate the neural network calculations, performing the parallel matrix operations that deep learning requires. Data flows through multiple stages. Low-latency search pipelines that identify candidates within seconds, offline analyses that perform more thorough parameter estimation over hours or days, and long-term studies that compare populations of events and search for statistical patterns. The low-latency pipeline is particularly demanding because it must keep pace with real-time data while maintaining high sensitivity. When a candidate event is identified, the system must quickly estimate the sky location, masses, and confidence level. Then distribute this information to partner observatories around the world. Every second of delay reduces the chance of catching short-lived electromagnetic counterparts like gamma-ray bursts. The pipeline uses a combination of matched filtering for initial detection, neural networks for rapid classification, and Bayesian inference for parameter estimation, all running in parallel on distributed computing resources. Graphics processors have become essential to this workflow because their architecture is ideally suited for the matrix operations that neural networks require. A modern GPU can perform thousands of parallel calculations simultaneously, exactly what's needed to evaluate a neural network with millions of parameters. For gravitational wave analysis, GPUs accelerate both the training of new models and the real-time inference needed for detection. Some research groups now use specialized AI hardware like Google's TPS or NVIDIA's latest architectures, optimized for transformer models and attention mechanisms. Transformer models, which revolutionized natural language processing, are now being adapted for gravitational wave analysis. These models excel at finding long-range dependencies in sequential data, making them potentially valuable for analyzing the extended time series of gravitational wave signals. Unlike convolutional networks that process local regions of data, transformers can attend to relationships between distant parts of the signal, potentially identifying subtle correlations that indicate the presence of a weak signal or specific source properties. Researchers at several institutions are exploring transformer architectures for waveform modeling and anomaly detection. The self-attention mechanism allows the model to weight different parts of the signal differently depending on context, focusing computational resources where they're most needed. Early results suggest that transformers can achieve similar detection performance to convolutional networks, while also providing better interpretability. The attention weights reveal which parts of the signal the model considers most important, giving insight into the decision-making process. Unsupervised anomaly detection represents another frontier in gravitational wave AI. Most current systems are trained to recognize specific types of signals: binary black hole mergers, neutron-star mergers, specific glitch types. But what about signals from sources we haven't predicted? The universe has a history of surprising us with phenomena that theorists didn't anticipate. Pulsars, gamma-ray bursts, fast radio bursts, all were discovered serendipitously rather than through targeted searches for predicted phenomena. Unsupervised learning algorithms can identify unusual patterns in data without being told what to look for. These systems learn a model of normal detector behavior, what the noise typically looks like, and flag anything that deviates significantly from this baseline. An autoencoder neural network, for instance, learns to compress data into a compact representation and then reconstruct the original signal. When fed normal noise, the reconstruction is accurate. But if the data contains an unusual feature, the autoencoder struggles to reconstruct it, and the reconstruction error signals an anomaly. Applied to gravitational wave data, this approach could identify exotic sources, cosmic strings, primordial black holes, gravitational waves from the early universe, or phenomena not yet imagined. The algorithm doesn't need to know what these signals look like in advance. It simply recognizes that they're different from the usual detector behavior. Of course, the challenge is distinguishing genuinely new astrophysical signals from instrumental glitches or rare noise fluctuations. But unsupervised methods provide a powerful complement to targeted searches. The detection of neutron-star mergers showcases the full power of multi-messenger astronomy enabled by rapid AI analysis. Unlike black hole mergers, which emit only gravitational waves, neutron-star collisions produce a spectacular electromagnetic display. When two neutron stars spiral together, their extreme densities and magnetic fields create conditions unlike anything else in the universe. The collision ejects neutron-rich matter that undergoes rapid nuclear reactions, synthesizing heavy elements through the R process. This ejected material is radioactive and glows across the electromagnetic spectrum, creating a kilonova explosion. GW 170817, detected in August 2017, was the first neutron-star merger observed through both gravitational waves and light. Meaning the gravitational wave signal lasted over 100 seconds as the two neutron stars, each about 1.4 times the Sun's mass, spiraled inward from an initial separation of a few hundred kilometers. The signal frequency swept from 30 Hz to over 1,000 Hz as the orbital period decreased from tens of seconds to milliseconds. Unlike black hole mergers, the neutron star's internal structure affects the gravitational waveform, imprinting information about the equation of state that describes matter at nuclear densities. Just 1.7 seconds after the gravitational wave signal ended, NASA's Fermi and Integral satellites detected a short gamma-ray burst from the same direction. This confirmed decades of theoretical predictions that neutron star mergers produce these mysterious high-energy flashes. Within 11 hours, optical telescopes identified a new point of light in galaxy NGC 4993, about 130 million light-years away. Over the following weeks, dozens of observatories tracked the kilonova's evolution, measuring its color, spectrum, and brightness, changes that revealed the physics of heavy element formation. The rapid identification and localization of the gravitational wave signal was crucial to this multi-messenger success. AI-enhanced analysis provided initial sky localization within minutes, narrowing the search area from the entire sky to a few hundred square degrees. As data from additional detectors became available, the localization improved further. Electromagnetic observers could prioritize galaxies within the localized region, dramatically increasing the chance of finding the optical counterpart. The kilonova spectrum showed clear signatures of heavy elements being synthesized in real time. Spectral features indicated the presence of lanthanides and other rare Earth elements created only in extreme neutron-rich environments. The total mass of gold and platinum produced exceeded Earth's entire mass, all created in a few seconds of nuclear burning. This observation confirmed that neutron star mergers are the universe's primary forges for elements heavier than iron, solving a decades-old mystery about where these elements come from. The gravitational wave signal also provided an entirely independent measurement of the universe's expansion rate. Because the signal's amplitude depends on distance, and the redshift of the host galaxy can be measured from its spectrum, GW 170817 served as a standard siren for cosmology. This measurement of the Hubble constant, the rate at which the universe expands, agreed with some previous determinations but differed from others, adding to a puzzle about why different methods give slightly inconsistent results. Future neutron star detections will refine this measurement, potentially resolving the tension. Population studies of black hole mergers reveal patterns that challenge theoretical models and raise profound questions about stellar evolution and black hole formation. LIGO and Virgo have now detected hundreds of black hole mergers, building a statistical picture of the black hole population. The mass distribution shows interesting features. A concentration around 8 to 10 solar masses corresponding to typical stellar black holes. A broader distribution extending to 50 solar masses or more, and a possible gap between neutron stars and black holes around 3 solar masses. Some black holes are unexpectedly massive. Stellar evolution models predicted that black holes from collapsing stars shouldn't exceed about 45 solar masses, because more massive stars lose mass through winds before they die. Yet LIGO has detected systems with component masses exceeding 60 solar masses, and even one event suggesting black holes around 85 solar masses. These discoveries suggest either that stellar wind models are incomplete, or that some black holes didn't form from stellar collapse, but through other mechanisms like hierarchical mergers or primordial formation in the early universe. The spin distribution also holds clues. Black holes can spin at rates up to the theoretical maximum, where the event horizon rotates at nearly the speed of light. The measured spins of merging black holes scatter across this range, with some systems showing high spins and others low spins or even retrograde spins, where the black hole rotation opposes the orbital motion. The pattern of spins constrains how black hole binaries form. In isolated binary star systems, spins should roughly align with the orbit, while dynamical formation in dense star clusters produces more random spin orientations. Some discoveries hint at exotic formation channels, hierarchical mergers, where the product of one merger later merges with another black hole, should produce systems with specific spin and mass signatures. AI algorithms trained on the population data search for statistical evidence of hierarchical mergers, comparing the observed distribution against models with different formation scenarios. Such preliminary evidence suggests that a fraction of detected mergers are indeed second or third generation events, black holes that have already merged at least once before. primordial black holes represent another intriguing possibility. These hypothetical objects would have formed in the first fraction of a second after the Big Bang from density fluctuations in the early universe, rather than from stellar collapse. If primordial black holes exist, they might constitute some or all of dark matter, the mysterious, invisible mass that dominates the universe's gravity. Detecting mergers of primordial black holes would revolutionize both cosmology and particle physics. But distinguishing them from stellar black holes is challenging. Their mass distribution might differ. Statistical properties of the merger rate evolution with redshift could provide clues. AI population synthesis codes model black hole formation, evolution, and mergers across cosmic time, predicting what mass and spin distributions different formation scenarios would produce. By comparing these predictions against the growing catalog of detections, researchers use machine learning to infer which models best match reality. This is a high-dimensional inference problem. The models have dozens of parameters describing stellar physics, binary evolution, supernova processes, and environmental factors. Bayesian neural networks and gradient-based optimization methods explore this parameter space efficiently, identifying regions consistent with observations and ruling out others. The gravitational wave background represents another detection frontier where AI plays a crucial role. This background consists of the incoherent superposition of gravitational waves from countless sources across cosmic history, mergers too distant or weak to detect individually, but collectively creating a stochastic background analogous to the cosmic microwave background radiation. The gravitational wave background carries information about the early universe, potentially including signals from cosmic inflation, phase transitions in the primordial plasma, or exotic phenomena from the first moments of existence. Detecting the background requires distinguishing it from detector noise, a challenge because both are stochastic and have no specific waveform to match. The strategy is to cross-correlate data from multiple detectors. The gravitational wave background should be correlated between detectors because they're seeing the same cosmic signal, while detector noise should be uncorrelated. Machine learning algorithms can identify subtle correlations that traditional statistical methods might miss, potentially reaching the sensitivity needed to detect the background years sooner than otherwise possible. In June 2023, pulsar timing arrays announced evidence for a gravitational wave background at very low frequencies, far below LIGO's band. These arrays monitored dozens of millisecond pulsars, using them as galaxy-scale gravitational wave detectors sensitive to waves, with periods of months to years. The detected background likely comes from supermassive black hole mergers, billion solar mass monsters colliding in distant galaxies. But confirming the source requires detailed modeling, and AI is helping to disentangle the gravitational wave signal from timing noise intrinsic to the pulsars themselves. Testing general relativity to unprecedented precision is one of LIGO's primary goals, and AI enhances these tests by enabling more accurate parameter estimation and more sensitive searches for deviations from Einstein's predictions. General relativity has passed every experimental test for over a century, but physicists expect it to break down under extreme conditions. The theory predicts its own incompleteness, singularities where curvature becomes infinite. Like the centers of black holes, he signaled that the theory requires modification or replacement by a quantum theory of gravity. Gravitational waves provide exquisite probes of strong field gravity. Near merging black holes, space-time curvature reaches values billions of times stronger than anywhere in the solar system. If general relativity fails under these conditions, gravitational wave signals would deviate from theoretical predictions in measurable ways. Researchers perform parameterized tests, modifying Einstein's equations in controlled ways and checking whether the data prefer the modifications or standard relativity. One powerful test examines the ring-down phase. After two black holes merge, the resulting black hole is initially distorted, aspherical. It quickly settles down by emitting gravitational waves at specific frequencies called quasi-normal modes, determined solely by the black hole's mass and spin. General relativity predicts precise relationships between different modes. If you measure the frequency and damping time of one mode, you can predict other modes exactly. Detecting multiple modes and verifying these relationships tests whether black holes truly behave as Einstein predicted. AI algorithms help extract weak ring-down modes from noisy data. The fundamental mode is typically the strongest and easiest to detect. But overtones, higher harmonics that ring at different frequencies, carry additional information. These overtones decay more quickly, making them harder to detect, but they probe the space-time structure closer to the event horizon. Machine learning systems trained on simulated ring-downs can identify these subtle features, achieving detection confidence sufficient to test the relationships between modes. The verification of Hawking's area theorem using gravitational waves exemplifies how AI-enhanced analysis enables precision fundamental physics. In September 2025, researchers announced they had verified Stephen Hawking's prediction that when black holes merge, the total surface area must always increase or remain the same, never decrease. Hawking predicted this in 1971, based on classical general relativity, and the area theorem is intimately connected to black hole thermodynamics and the ultimate fate of information that falls into black holes. Using AI-enhanced analysis of an exceptionally clear signal detected on January 14, 2025, designated GW 250114, researchers confirmed this prediction with 99.999% confidence. And the signal had a signal-to-noise ratio of nearly 80, far higher than typical detections, providing an unprecedented view of the merger dynamics. The two initial black holes had a combined surface area of about 240,000 square kilometers, roughly the size of Oregon. After the merger, the final black hole's area increased to 400,000 square kilometers, about the size of California. This measurement required extracting masses and spins of the black holes before and after merger from the gravitational wave signal, then calculating the area of the event horizons. The area of a black hole's event horizon depends on both mass and spin through a formula that general relativity specifies precisely. For a non-rotating black hole, the area is proportional to the mass squared. For a rotating black hole, the relationship is more complex, but still determined entirely by mass and spin. The challenge is that gravitational wave signals don't directly reveal mass and spin. These parameters must be inferred from the waveform's detailed shape. Traditional parameter estimation uses Markov chain Monte Carlo methods that explore parameter space through random walks, guided by probability gradients. But these methods are computationally expensive, often requiring days of computing time for a single event. AI-based parameter estimation accelerates this process by orders of magnitude. Researchers train neural networks on hundreds of thousands of simulated signals, teaching the network to map from observed waveforms to source parameters directly. Once trained, the network can perform parameter estimation in seconds rather than days, with comparable accuracy to traditional methods. For the area theorem verification, this speed allowed researchers to perform extensive consistency checks and statistical tests that would have been prohibitively expensive with traditional approaches. Kip Thorne, one of LIGO's founders, noted that Hawking had called him immediately after the first gravitational wave detection in 2015 to ask whether LIGO might be able to test his area theorem. Hawking passed away in 2018, sadly before seeing his prediction observationally confirmed. But the verification stands as a beautiful tribute to his theoretical insights and demonstrates the power of combining theoretical brilliance with experimental ingenuity and modern computational tools. Looking ahead, the next generation of gravitational wave detectors will rely even more heavily on artificial intelligence, not just for data analysis, but as integral components of detector design and operation. The proposed facilities represent a massive increase in capability, sensitivity, and data volume that will fundamentally transform gravitational wave astronomy from detecting individual events to conducting population surveys and precision cosmology. Cosmic Explorer, planned for construction in the United States in the 2030s, will be the most sensitive ground-based detector ever built. With 40-kilometer arms, 10 times longer than LIGO, and advanced technologies including cryogenic mirrors, quantum squeezing, and next-generation lasers, Cosmic Explorer will detect black hole mergers throughout the entire observable universe. Every stellar black hole merger that has ever occurred anywhere in cosmic history will be detectable. The detector will observe neutron star mergers out to redshift 5, corresponding to when the universe was just 1.2 billion years old. This sensitivity comes with profound implications. Cosmic Explorer will detect tens of thousands of binary black hole mergers per year, building exquisite statistics on the mass distribution, spin distribution, and merger rate as a function of redshift. This population data will constrain how stars form, evolve, and die across cosmic time, how binary systems evolve, and how galaxies grow. The sheer volume of data will necessitate AI-driven analysis. Human inspection of every event will be impossible. The Einstein telescope, planned for construction in Europe, takes a complementary approach with an underground triangular detector and multiple interferometers operating at different frequencies. The triangular geometry with three 10-kilometer arms allows simultaneous measurement of both gravitational wave polarizations, providing better sky localization and enabling more stringent tests of general relativity. The underground location provides exceptional seismic isolation, and cryogenic mirrors cooled to 10 Kelvin will reduce thermal noise to negligible levels. Einstein telescope will be particularly powerful for low-frequency gravitational waves, observing the early and spiral phase of binary systems hours or days before merger. This early warning capability would allow electromagnetic telescopes to point toward the source before the merger occurs, catching transient phenomena that might otherwise be missed. AI systems will process the continuous data stream on identifying promising candidates and issuing alerts with increasing confidence as systems spiral closer together. Both detectors will contribute to the global network that will also include LIGO India, an advanced detector currently under construction that will significantly improve sky localization for all detected events. With 5 sensitive detectors spread across the globe, triangulation will pinpoint source locations to a few square degrees or better, enabling targeted follow-up observations and detailed studies of electromagnetic counterparts. But even these ambitious ground-based detectors have fundamental limitations. Seismic noise makes it impossible to detect gravitational waves below about 10 Hz on Earth's surface, and low-frequency waves carry unique information about massive black holes and the early universe. This is where space-based detectors enter the picture. The Laser Interferometer Space Antenna, LISA, will launch in the 2030s as a constellation of 3 spacecraft flying in formation 2.5 million kilometers apart, forming a giant triangle in space. LISA will detect gravitational waves from 0.1 MHz to 1 Hz, frequencies completely inaccessible to ground-based detectors. This band is rich with sources: supermassive black hole mergers, extreme mass ratio and spirals where stellar mass objects spiral into million solar mass black holes, verification binaries in our galaxy, and potentially exotic sources like cosmic strings or primordial gravitational waves from inflation. Supermassive black hole mergers will be LISA's headline discoveries. Every galaxy contains a supermassive black hole at its center, and when galaxies merge, their black holes eventually coalesce. These mergers involve black holes millions to billions of times the Sun's mass, producing gravitational waves so powerful they'll be detectable across the entire universe. LISA will observe the complete merger history of supermassive black holes, tracing how the largest structures in the cosmos assembled over cosmic time. Extreme mass ratio and spirals provide unique tests of general relativity. When a stellar mass black hole or neutron star orbits near a supermassive black hole, it follows a complex trajectory through highly curved spacetime, gradually spiraling inward over thousands of orbits. The gravitational wave signal maps the space-time geometry around the supermassive black hole with exquisite precision, revealing whether the black hole has the exact properties Einstein predicted or whether deviations indicate new physics. The computational challenge of modeling extreme mass ratio and spirals is extraordinary. The orbits aren't simple ellipses, but rather complex geodesics through curved space-time, precessing and changing shape as they shrink. Calculating the gravitational waveform requires solving Einstein's equations using sophisticated perturbation theory and numerical methods. A single waveform can take weeks to compute, and covering the parameter space requires millions of templates. This is exactly where AI becomes essential. Neural networks can learn to generate approximate waveforms thousands of times faster than numerical simulations, enabling the template banks needed for detection and parameter estimation. Surrogate models trained on libraries of numerical waveforms can interpolate accurately across parameter space, providing the speed needed for real-time analysis while maintaining the accuracy needed for scientific inference. LISA will also detect galactic binaries, pairs of white dwarfs, neutron stars, or stellar black holes orbiting each other in our own galaxy. Tens of thousands of these systems will be observable, creating a persistent foreground of overlapping signals. Disentangling this confusion requires sophisticated signal processing, identifying individual systems within the collective signal. AI clustering algorithms and source separation techniques, adapted from audio processing, will parse the data, extracting information about binary populations in the Milky Way. The LISA mission will generate continuous data streams over multiple years, requiring automated monitoring and analysis. Machine learning systems will flag instrumental glitches, identify interesting events for detailed study, and manage the computational resources devoted to different analysis tasks. The spacecraft themselves will use AI for autonomous operations, optimizing laser pointing, formation control, and data compression. Even beyond LISA, more ambitious concepts are being explored. The Big Bang Observer would push into even lower frequencies, detecting gravitational waves from cosmic inflation itself. The Daisy-Hertz Observatory would fill the gap between LISA and ground detectors, observing intermediate mass black hole mergers and providing early warning for events that LIGO and Einstein telescope will later detect. When all of these concepts rely on AI for feasibility, using machine learning to handle data rates and complexity that would otherwise be overwhelming. The computational infrastructure supporting this detection network represents a remarkable achievement in scientific computing. Data from detectors around the world flows to analysis centers, where GPU clusters and supercomputers perform continuous signal processing. The low-latency pipeline combines multiple detection algorithms running in parallel, cross-checking results to minimize false alarms. Rapid parameter estimation provides initial sky localization for electromagnetic follow-up. Offline analysis performs more thorough investigations, running for days or weeks to extract every possible piece of information from important events. Cloud computing resources now augment dedicated facilities, providing elastic scaling to handle computational surges when interesting events are detected or when training new neural network models. Distributed databases store petabytes of detector data, waveform templates, and simulation results, with intelligent caching and prefetching to optimize data access patterns. The entire system coordinates through sophisticated workflow management software that schedules jobs, manages dependencies, and ensures that critical alerts are processed with priority. This infrastructure handles not just detection, but also simulation and model development. Numerical relativity simulations continue to produce new waveform libraries, expanding parameter space coverage and improving accuracy. And these simulations now incorporate complex physics beyond pure gravity. The effects of matter in neutron star mergers, electromagnetic fields, and potentially even nuclear physics, if simulations reach sufficient resolution. Each refinement improves the precision of parameter estimation and our ability to extract astrophysical information from gravitational wave signals. The role of AI extends even to generating these expensive simulations more efficiently. Surrogate models trained on existing simulation results can predict waveforms for new parameter combinations without running full simulations, accelerating the process by factors of thousands. Active learning algorithms identify which regions of parameter space most urgently need new simulations to improve model accuracy, optimizing the use of computational resources. Physics-informed neural networks incorporate Einstein's equations directly into the network architecture, ensuring that predictions satisfy fundamental physical constraints. Some researchers are exploring whether AI could eventually solve Einstein's equations directly, replacing numerical relativity simulations entirely. This is an extraordinarily ambitious goal, because Einstein's equations are some of the most challenging in all of physics. Recent progress using neural operators and transformer architectures hints that this might eventually be possible, at least for certain classes of problems. Success would revolutionize gravitational wave astronomy by making waveform generation essentially instantaneous and enabling real-time parameter space exploration. The partnership between human intelligence and artificial intelligence has become central to gravitational wave astronomy. With each contributing unique strengths, human researchers provide physical intuition, creative hypotheses, and the ability to recognize when results don't make sense or when new approaches might be fruitful. We excel at synthesizing information across disparate fields, drawing connections between gravitational wave observations and insights from nuclear physics, stellar evolution, galaxy formation, and cosmology. We ask the profound questions that drive science forward. What are black holes really? How did the universe begin? Are there new laws of physics waiting to be discovered? AI systems provide complementary capabilities that are equally essential. They process vast data streams without fatigue, maintaining vigilance across the years of continuous observation. They find subtle patterns in noise that would escape human attention, detecting signals too weak or unusual for traditional methods. They explore high-dimensional parameter spaces systematically, identifying optimal configurations that human intuition might never consider. They scale effortlessly from analyzing a single event to synthesizing information across thousands of detections, building statistical insights that reveal cosmic population trends. The most powerful results emerge from combining these strengths. Humans design the questions and interpret the results, while AI handles the computational heavy lifting. Researchers develop theoretical models predicting what gravitational waves from various sources should look like. And AI systems search for these signatures in the data with superhuman speed and sensitivity. When unexpected features appear, human scientists investigate, formulating hypotheses that AI can test through rapid analysis of existing data and simulations. This collaboration has already revealed aspects of the universe that neither humans nor AI could have discovered alone. The very first gravitational wave detection exemplifies this. Human vision and decades of theoretical development conceived of LIGO and predicted what signals would look like, while algorithms processed the data in real time and flagged the historic signal within minutes. The subsequent months of careful analysis combined human judgment about systematic uncertainties with AI's ability to evaluate millions of synthetic waveforms to verify that the signal was real and extract its properties. As we look to the future, this partnership will only deepen. Next-generation detectors will produce data streams rich beyond anything currently imaginable, with thousands of detections per year and continuous monitoring of the gravitational wave sky. Human oversight will remain crucial for quality control, hypothesis generation, and scientific interpretation. But AI will be absolutely essential for managing the data volume and extracting maximum information. The societal implications extend beyond astronomy. The techniques developed for gravitational wave analysis have applications across science and technology. Deep learning methods for signal detection in noise-benefit medical imaging, where weak diagnostic signals must be extracted from complex biological backgrounds. AI optimization of complex systems informs everything from power grid management to climate modeling. The computational infrastructure and software frameworks developed for gravitational wave analysis are being adapted for particle physics, genomics, and other data-intensive fields. There are also important ethical considerations as AI becomes more central to scientific discovery. When machine learning systems make critical decisions, flagging events for follow-up, classifying signals as real or false, estimating parameters that inform theoretical conclusions. How do we ensure these decisions are sound? The black box nature of some neural networks poses challenges for scientific transparency. We need to understand not just what the AI concludes, but why. To verify that conclusions rest on valid physical reasoning rather than spurious correlations in training data, researchers are developing explainable AI techniques specifically for gravitational wave analysis. Attention visualization shows which parts of a signal influence the network's decision, revealing whether it's focusing on physically meaningful features. Adversarial testing probes whether networks can be fooled by carefully constructed fake signals, checking robustness. Comparison against traditional methods on well-understood examples verifies that AI conclusions are consistent with established physics. Where these validation steps build confidence that AI systems are truly discovering astrophysical phenomena rather than artifacts. Another consideration is the potential for automation bias, the tendency to trust AI decisions uncritically. Even sophisticated machine learning systems can fail in unexpected ways when encountering situations that differ from their training data. Maintaining healthy skepticism and validation protocols ensures that human judgment remains in the loop for critical decisions. The goal is not to replace human scientists, but to augment their capabilities, handling routine tasks and data volume while escalating unusual or ambiguous cases for expert review. The training data used to develop AI systems also deserves scrutiny. If simulations used for training don't adequately cover the full range of possible astrophysical sources, the resulting models may miss unexpected signals. Researchers address this through diverse training sets that include not just vanilla binary mergers, but also exotic scenarios, eccentric orbits, extreme mass ratios, precessing spins, matter effects. Unsupervised learning methods complement supervised approaches, providing a safety net for truly unexpected phenomena that no training data anticipated. As we push toward more ambitious detectors and more sophisticated AI, we're entering an era where machines will help us discover phenomena we cannot currently imagine. The history of astronomy teaches us that every new way of observing the universe reveals unexpected wonders. Radio astronomy discovered pulsars and cosmic microwave background radiation. X-ray astronomy found black hole accretion disks and galaxy clusters. Infrared astronomy revealed dusty star-forming regions and distant galaxies obscured by dust. Gravitational wave astronomy is barely a decade old, yet it has already discovered black hole populations we didn't know existed, confirmed neutron star merger kilonova production, and enabled precision tests of fundamental physics. What will we find in the next decade as detector sensitivity improves by another order of magnitude? Will we detect gravitational waves from supernova explosions, revealing the asymmetric collapse of massive stars? Will we discover intermediate mass black holes in dense star clusters, filling the gap between stellar and supermassive black holes? Will we detect cosmic strings, topological defects from the early universe predicted by some theories but never observed? Will we find evidence for extra dimensions of space through deviations from general relativity in extreme gravitational fields? Or will we discover something completely unexpected, a phenomenon that current theory doesn't predict and human intuition hasn't imagined? AI systems trained to recognize anomalies might be our best chance of catching these surprises. By continuously monitoring the gravitational wave sky and flagging anything unusual, machine learning provides an alert system for the unknown. When such anomalies appear, human creativity will be essential for formulating explanations and designing observations to test hypotheses. The expansion of gravitational wave astronomy also connects to broader questions about our cosmic origins and destiny. Gravitational waves carry information about the earliest moments of the universe, potentially including echoes of cosmic inflation, the exponential expansion that seeded all structure we see today. Detecting primordial gravitational waves would reveal physics at energy scales trillions of times higher than particle accelerators can reach, opening a window on fundamental interactions that shaped reality itself. Black hole mergers across cosmic time tell the story of how structure formed and evolved. The first stars, forming just 100 million years after the Big Bang, were massive and short-lived, leaving black holes that may have seeded supermassive black hole growth. Gravitational waves from their mergers carry fossil evidence of this era. By measuring how the merger rate changes with redshift, how it varies as we look back through cosmic history, we reconstruct the evolution of stellar populations, star formation rates, and the assembly of galaxies. Neutron-star mergers constrain the equation of state of nuclear matter at densities beyond anything achievable in laboratories. The interior of a neutron star is the densest stable matter in the universe, where atomic nuclei are compressed to the point of touching and potentially transitioning to exotic states like quark matter. The gravitational wave signal from neutron star mergers encodes information about how matter behaves under these extreme conditions, informing both nuclear physics and our understanding of supernova mechanisms. The measurement of cosmic expansion through gravitational wave standard sirens may eventually resolve current tensions between different methods. The Hubble constant inferred from the cosmic microwave background differs slightly from direct measurements using supernovae and other standard candles. This discrepancy might indicate new physics. Perhaps dark energy evolves with time, or unknown particles interact in ways that affect the expansion rate. Gravitational wave sirens provide an independent check, and as detections accumulate, the precision will rival or exceed other methods. Multi-messenger observations combining gravitational waves, electromagnetic radiation, and potentially even neutrinos will provide the most complete picture of cosmic phenomena. Each messenger carries complementary information. Gravitational waves reveal bulk mass motion and orbital dynamics. Gamma rays probe high-energy particle acceleration. Optical and infrared light shows radioactive decay and material composition. Neutrinos signal nuclear reactions in dense matter. By observing the same event across all these channels, we achieve a holistic understanding impossible from any single messenger. The infrastructure for multi-messenger astronomy is growing rapidly. Alert systems automatically notify observatories worldwide when gravitational waves are detected, triggering immediate follow-up observations. Machine learning coordinates these observations, prioritizing targets based on scientific importance, sky localization, uncertainty, and the likelihood of electromagnetic counterparts. As the detection rate increases, resource allocation becomes increasingly important. Not every gravitational wave event can receive intensive electromagnetic follow-up, so AI helps identify the most promising candidates. This global scientific enterprise represents international collaboration on an unprecedented scale. LIGO, Virgo, Kagra, and future detectors operate as a single integrated network, sharing data and combining observations. Thousands of researchers across dozens of countries contribute to the analysis, organized through the LIGO Scientific Collaboration and Virgo Collaboration. The data is ultimately public, available to the entire scientific community, and enabling independent verification of results. This openness, combined with rigorous peer review, ensures that gravitational wave astronomy maintains the highest standards of scientific integrity. The technological legacy of gravitational wave detection extends far beyond astronomy. The precision manufacturing techniques developed for LIGO's mirrors benefit industries requiring ultra-stable optical components. The vibration isolation systems inform designs for sensitive scientific instruments and precision manufacturing equipment. The high-power laser technology finds applications in materials processing and manufacturing. The vacuum technology transfers to semiconductor fabrication and other high-tech industries. The computational methods developed for data analysis contribute to machine learning research that benefits countless other fields. Educational impacts are equally significant. Gravitational wave astronomy inspires students to pursue careers in physics, engineering, and computer science. The combination of fundamental physics, cutting-edge technology, and profound discoveries about the universe captures imaginations and demonstrates the value of sustained investment in basic research. Universities and research institutions involved in gravitational wave detection report increased student interest and enrollment in related programs. Public outreach activities reach millions, bringing the excitement of scientific discovery to people worldwide. Looking forward to the next several decades, we can envision a future where gravitational wave observatories operate continuously across the globe and in space, forming an integrated network that monitors the cosmic gravitational wave sky with exquisite sensitivity. Some AI systems will process the data streams in real time, identifying thousands of events per year and classifying them by source type, distance, and scientific importance. Automated alerts will trigger multi-messenger campaigns, with robotic telescopes and satellite observatories coordinating observations of electromagnetic counterparts. The accumulated data will enable population synthesis on a vast scale, revealing how black holes and neutron stars are distributed across mass, spin, and cosmic time. We'll measure the star formation history of the universe through its gravitational wave signature. We'll trace the growth of structure from the first stars to present-day galaxies. We'll test general relativity in regimes where quantum effects might become important, searching for hints of the quantum theory of gravity that must eventually replace Einstein's classical description. In this future, AI will be an indispensable partner, but human insight will remain central. The questions driving research will emerge from human curiosity about our origins, our place in the cosmos, and the fundamental laws governing reality. The interpretation of results will require human judgment, synthesizing gravitational wave observations with insights from across physics and astronomy. The decision of which new detectors to build, which observations to prioritize, which theoretical models to pursue, these will remain fundamentally human choices, guided by scientific intuition and collective wisdom. Yet the pace of discovery will be set by the symbiosis between human and artificial intelligence. Algorithms will find patterns that human intuition would miss. Simulations will explore parameter spaces too vast for human imagination. Optimizations will push detector performance beyond what human engineers could achieve alone. The partnership leverages the unique strengths of biological and artificial cognition, creating capabilities that exceed either in isolation. As we stand at this moment in history, barely a decade into the gravitational wave astronomy era, we're witnessing the birth of a new way of understanding the universe. Space-time itself has become our messenger, carrying news of cosmic violence across billions of light years and billions of years of time. Every detected gravitational wave is a message from the distant past, a signal that has traveled through expanding space while galaxies formed. Stars were born and died, and ultimately, while life emerged on a small planet orbiting an unremarkable star, the black holes colliding in the depths of space, sending their gravitational whispers across the cosmos, have found the perfect hunters in artificial intelligence systems that never sleep, never tire, and continuously learn to better hear the symphony of space-time itself. These machines, designed and directed by human intelligence, augment our senses and extend our reach across the universe in ways our ancestors could never have imagined. Together, human creativity and machine precision, biological insight and digital computation, scientific intuition and algorithmic analysis, we are reading the history written in gravitational waves, decoding the story of black holes, neutron stars, and perhaps phenomena yet to be discovered. The universe is speaking in the language of warped space-time, and we have learned to listen. Every new detection adds another verse to the cosmic poem, revealing beauty and violence, order and chaos, familiar physics and mysterious anomalies. As our detectors grow more sensitive and our AI systems more sophisticated, we will hear fainter signals from more distant events, pushing back through cosmic history toward the very beginning of time. Perhaps we will eventually detect the faint echo of inflation itself, the moment when the universe explosively expanded from quantum fluctuations to cosmic scales. Perhaps we will find signatures of extra dimensions or new forces, physics beyond the standard model that has eluded particle accelerators. Perhaps we will discover something we cannot currently imagine, a phenomenon so unexpected that it reshapes our understanding of reality. Whatever we find, the journey will be a collaborative adventure between the human mind, creative, intuitive, driven by curiosity about existence itself, and artificial intelligence. Tireless, precise, capable of perceiving patterns in data that would otherwise remain hidden. This partnership represents more than just a practical arrangement for processing data. It embodies a profound truth about discovery in the modern age. The universe is too vast, too complex, too subtle for unaided human perception to fully comprehend. But augmented by machines that extend our senses and amplify our analytical capabilities, we become capable of apprehending cosmic truths that would otherwise remain forever beyond our grasp. The gravitational waves rippling through space-time carry stories of events so extreme that they strain the limits of physical law. Black holes merging with a violence that briefly outshines all the stars in the observable universe. Neutron stars colliding to forge the heavy elements that make up planets and life. Potentially, signals from the birth of the universe itself or from exotic phenomena that current theory doesn't predict. Each wave is both a scientific dataset and a cosmic narrative. Physics and poetry intertwined as we venture further into this journey. As Cosmic Explorer and Einstein Telescope and LISA push the frontiers of sensitivity, as AI systems grow more sophisticated and capable, we approach a future where gravitational wave astronomy becomes as routine and comprehensive as optical astronomy is today. We will have catalogs of millions of black hole mergers. We will track supermassive black holes coalescing across the entire history of cosmic structure formation. We will measure the expansion of the universe and the properties of matter with precision limited only by fundamental physics. We will test Einstein's theory to accuracies he never imagined possible. But numbers and precision, while valuable, are not the essence of this endeavor. At its heart, gravitational wave astronomy represents humanity's relentless drive to understand the universe and our place within it. Every civilization that has gazed at the stars has wondered about the nature of reality, the origin of existence, the ultimate fate of all things. We pursue these questions not because they offer practical benefits, though those often emerge unexpectedly, but because we are conscious beings capable of contemplating our own existence, and that contemplation demands we seek deeper understanding. The tools we build, LIGO's mirrors suspended in perfect isolation, kilometers of laser light probing the fabric of space, neural networks learning to recognize the signatures of cosmic catastrophe, are extensions of this fundamental drive. They represent our refusal to accept the limitations of our biological sensors, our determination to perceive what nature has hidden from direct experience. We cannot see gravitational waves with our eyes or hear them with our ears, but through ingenuity and persistence, through mathematics and engineering, and now through artificial intelligence, we have made them perceptible. We have taught machines to detect the imperceptible and alert us to cosmic events we would otherwise never know occurred. The partnership between human and artificial intelligence in this endeavor points toward the future of science more broadly. As problems grow more complex and datasets more vast, collaboration between biological and digital cognition will become increasingly essential. Humans will continue to provide the vision, the creativity, the ability to ask profound questions, recognize when answers don't make sense, I will increasingly handle the detailed execution, the processing of vast information streams, the exploration of complex parameter spaces, the optimization of systems too intricate for human comprehension. Now, this is not the replacement of human intelligence, but rather its amplification and augmentation. The human mind remains irreplaceable for the tasks it evolved to perform. Pattern recognition across disparate contexts, creative hypothesis generation, ethical reasoning, finding meaning and significance in discovery. AI systems excel at tasks that are fundamentally computational, processing data, evaluating mathematical models, optimizing complex systems. Together, these capabilities create a whole greater than the sum of its parts, enabling discoveries that neither humans nor machines could achieve alone. The gravitational waves passing through Earth at this very moment carry information about black holes colliding billions of light years away, events that occurred when the universe was young and different, before our solar system existed, before life emerged anywhere in our galaxy. These waves have traveled across expanding space for cosmic ages, encoding in their oscillations a complete record of the violent events that created them. Now, finally, after their unimaginably long journey, they encounter LIGO's mirrors and Virgo's interferometers and Cagra's arms, causing displacements smaller than an atomic nucleus, distortions so minute that they seem impossible to detect. Yet we detect them, our instruments, guided by human ingenuity and AI precision, capture these whispers from the depths of space and time. Each detection is a triumph of human imagination and technological capability, a demonstration that with sufficient creativity and persistence, we can perceive and understand phenomena far beyond our ordinary experience. Each detection is also a reminder of how much remains unknown. The universe is vast beyond comprehension, filled with phenomena we have yet to discover. Gravitational wave astronomy is still in its infancy. We have just begun to explore what this new window on the cosmos reveals. In the coming years and decades, as our detectors improve and our AI systems mature, we will undoubtedly uncover surprises that challenge current theories and expand our understanding. We will likely find some answers to long-standing questions. How do supermassive black holes grow? What is the equation of state of nuclear matter? Is general relativity truly exact, or do subtle deviations hint at deeper theories? But we will certainly also encounter new mysteries, phenomena that demand novel explanations and fresh theoretical insights. This is the nature of scientific exploration. Each answer spawns new questions. Each discovery reveals how much more remains to be discovered. The partnership between human and artificial intelligence ensures that we can pursue these questions effectively, combining human creativity with computational power to push the boundaries of knowledge ever outward. The machines hunting for colliding black holes in spacetime are not merely tools, but collaborators in this grand endeavor, partners in humanity's quest to comprehend the cosmos. And so the symphony continues. Across the universe, black holes merge and neutron stars collide, sending gravitational waves racing through space-time at the speed of light. Most pass unnoticed through empty space, their subtle distortions affecting no one and nothing. But some, after journeys spanning billions of light years and billions of years, encounter a small planet where curious beings have built exquisitely sensitive instruments. There, finally, they are detected, measured, analyzed, and understood. There, finally, the cosmic violence that created them finds witnesses capable of appreciating the profound physics at play. The transformation that AI has brought to gravitational wave astronomy extends beyond mere efficiency gains or processing speed. It represents a fundamental shift in how we conduct observational science, from reactive detection to predictive monitoring, from analyzing individual events to conducting comprehensive cosmic surveys. Machine learning systems now continuously evaluate the probability of detection across different regions of parameter space. predicting where the next discovery might come from based on population models and detection statistics. These predictions guide observing strategies, helping researchers decide when to push detector sensitivity at the expense of stability, or when to prioritize reliability over maximum range. The AI becomes not just an analytical tool, but a strategic partner in the scientific process, helping optimize how we allocate limited observational resources across an infinite universe of possible targets. This represents a maturation of the field from its heroic early days of hunting for any signal at all, to a more sophisticated era where we can afford to be selective. We are those witnesses. We stand at a unique moment in the history of the universe. Conscious beings capable of detecting and decoding gravitational waves, capable of building machines that amplify our perception and analysis, capable of understanding, at least partially,